Finding the Coriolis acceleration for complex motion of the material point. Article 9.5 of the book Mechanical Systems Calculations of the Marine Facilities. Little bit about the complex motion, about the accelerations and velocities determined in the complex motion. Theorem of the velocities addition of point of in the complex motion. In the complex motion, the complex is if we consider one coordinate system, another one coordinate system, which another one moving. The first one fixed coordinate system. The motion in the fixed coordinate system described as the absolute motion, and the motion within the moving coordinate system described as the relative motion, and the motion mean relative to the moving coordinate system, and the motion of the moving coordinate system itself relative to the fixed coordinate system is the transfer motion. So we have three motions: absolute motion relative to the fixed coordinate system, the transfer motion, that is the motion of the moving coordinate system relative to fixed one, and the relative motion, that is the motion of the point within the moving coordinate system. In the complex motion, the absolute velocity of point is equal to the vector sum of the point transferring and relative velocities. So the relative velocity is velocity of the point in the moving coordinate system, that is relative the moving coordinate system velocity, and this is transfer motion, the velocity of the motion of the transfer coordinate system relative to the fixed one. This is theorem of velocities addition. This theorem of addition of the accelerations of the point in complex motion, so-called Coriolis theorem. In the complex motion, the absolute acceleration A, the vectors, magnitudes of a moving point is equal to the vector of transferring, acceleration transferring, that's acceleration of the motion of the moving coordinate system, the relative one acceleration, that's acceleration of the point within the moving coordinate system, the relative acceleration, and the Coriolis acceleration. Coriolis is acceleration, the third sum. So we have three sums for the acceleration in the complex motion of the point is in the coordinate system. The Coriolis acceleration vector is determined by the product, by the vector product, the transfer angular velocity, that is angular velocity of the moving coordinate system when it moves within the fixed coordinate system. So this angular velocity of moving coordinate system relative the fixed coordinate system, and the relative translational velocity of the point in a moving coordinate system. And by the vector product, we can find, we have not the vector product, we have the doubled vector product, the Coriolis acceleration equal to doubled vector product of angular velocity transfer and of the moving coordinate system within the fixed coordinate system, and the translational velocity of the point in the moving coordinate system. And we can find the Coriolis acceleration magnitude as we have two factors of the formula of the Coriolis acceleration multiplied by the angular magnitude of the angular velocity of moving coordinate system rotation in the fixed coordinate system by the magnitude of the progressive translational velocity of the point in the moving coordinate system, and by sine alpha. Alpha is the angle of the inclination. Angle, I'm sorry, not inclination, but angle between the vectors of the angular velocity, transfer angular velocity, and the relative translational velocity in the moving coordinate system, sine alpha. So the question arises when for example, in particular cases, the Coriolis acceleration is to be equal to 0. For example, it could be equal if the magnitudes of the transfer angular velocity is equal to 0. That's one case. That's one. If the translational velocity of the point in the moving coordinate system equal to 0, or if the sine alpha is equal to 0. What does mean that equality to 0? The transfer angular velocity. That means that the moving coordinate system does not rotate in the fixed coordinate system. That is equality to 0 of the angular velocity of the transfer coordinate system, of the moving coordinate system, equality to 0 of transfer angular velocity. At the absence of the relative motion, that is, if the point does not move in the moving coordinate system. So then as well we have Coriolis acceleration have to be equal to 0. And if the vectors of the angular velocity and the vector of the transfer angular velocity and the vector of the relative progressive or translational velocity are parallel. If the sine alpha is equal to 0, when the alpha angle is equal to 0 or equal to the pi is pi radian, 180 degrees sine alpha. So if the forces, excuse me, not forces, but the vectors, the vector angular velocity, usually we use the right screw rule to find the direction of the vector. If we have the rotation, we can inside the right screw with the rotation, with the rotation of the any body, or in definite one case, we coincide with the rotation of the moving coordinate system, for example, to find the transfer angular velocity. Then the motion of the right screw will coincide to the positive direction of the angular velocity. That is direction of the vector of the transfer angular velocity. And the translational velocity direction is understandable, which is the vector due to the direction of the moving of the point in the moving coordinate system. So the absence of the relative motion, when the relative translational velocity or progressive velocity equal to 0, and when the angle is equal to 0 or equal to 180 degrees or pi. Next, let's consider the rule to find the direction of the vector of the Coriolis acceleration. Specific acceleration. This acceleration arises when we consider the complex motion. Complex motion of the material point means that the material point moves in the moving coordinate system. So we have the moving coordinate system, and we have the point moving in the moving coordinate system, and we have the elements of the motion of the coordinate system itself, and we have the elements of the motion of the point within the moving coordinate system. So the question arises how to find the elements of the motion. Elements of the motion mean the velocities, angular velocities and accelerations, angular accelerations, not for the angular accelerations for the point, but just the accelerations in the coordinate system, absolute motion relative to the fixed coordinate system, or in the relative motion, etc. So first of all, the direction of the Coriolis acceleration we can find using the rule to find the direction of the vector product. If we have vector product of the vector of the transfer angular velocity and the vector of translational velocity relative, so we multiply these two vectors, and the angle alpha is between these two vectors. So to multiply, how to find the direction of the Coriolis acceleration. Just if we rotate the vector of the angular velocity, the first factor in the vector product, to the vector of the translational velocity, this is a second factor. The sequence of the factors is important for finding the direction of the Coriolis acceleration. Sequence of factors in the vector product, finding the angular acceleration, non-angular acceleration, finding the acceleration of the Coriolis. This is translational acceleration, exactly, progressive translational acceleration. Then in the perpendicular direction, perpendicular to the plane of the location of two vectors, perpendicular to the plane of the location of the angular transfer angular velocity vector and the translational velocity relative vector in the moving coordinate system of the point. In these two vectors, we have the plane perpendicular to this plane. We, in the same point of these two vectors beginning, we can find the perpendicular directions if we rotate the vector of the transfer angular velocity to the vector of the relative translational velocity of the point. The right screw will be directed, right screw, if it moves, when the screw rotates, this screw will move to the positive direction of the vector of the Coriolis acceleration, Coriolis translational acceleration, yes. Another rule we have, the so-called Zhukovsky rule is indicated how to find the direction of the Coriolis acceleration on the figure 951b. This sometimes it's more convenient to use the Zhukovsky rule to find direction of the Coriolis acceleration. To do that, first we have to find the projection of the vector of the translational velocity relative onto the plane perpendicular to the vector of the transfer angular velocity of the rotation of the moving coordinate system within the fixed coordinate system absolute. So having this projection, after that we have to turn the counterclockwise, watching towards the transfer angular velocity vector towards when we watch, we can to rotate this projection on the plane perpendicular to this vector of the angular velocity transfer. We have rotated this component of the translational relative velocity of the point in the moving coordinate system. If we rotate it to the for 90 degrees counterclockwise, watching towards the axis of the transfer angular velocity. So we will rotate in this vector. We will find the direction of the Coriolis acceleration. That is a second way. This rotation for 90 degrees. 90 degrees is 50. This is pi divided by 2. So this is another practical rule to find the direction of the Coriolis acceleration. So one example, let's consider the exercise. If, for example, the point, definite material point, moves over the surface of the globe. This is the globe, the surface of the globe, the coordinate system, Cartesian x, y, z. So it can move in another direction on this. So it can move around the equator of definite relative velocity, around the meridian, by the meridian, it can move with definite velocity as well, relative. So relative in the system moving, the system coordinate moving associated with definite one point on the surface of Earth, of the globe. And just a little bit about the angular velocity, magnitude of transfer angular velocity of rotation of the Earth. It is, we can find is 2 by pi and 24 hours a day and 360 seconds per 1 hour. So we can find that the angular velocity of rotation of Earth is 7.272 multiplied by 10 power to power minus 5 the radian per second. This is not big angular velocity. Anyway, this can cause the noticeable definite magnitude of the Coriolis acceleration if any body, any point, a material point moves in parallel to the surface of the Earth. It could be the flying object, etc. Using the formula for finding the Coriolis acceleration, we define the angle between the vectors of the angular velocity and the translational velocity of the point moving over by the Earth's surface. The sign between the angles correspond to the latitude phi. We can phi angle here to this radius of the Earth. This is latitude. This is direction of the positive direction of the transfer angular velocity. This is magnitude of the angular velocity. This is north. This is south. This is east, west. So when moving point along the meridian at the pole, along the meridian at poles, sine phi equal to 1. So if phi is equal to 90 degrees, or pi divided by 2 phi on the poles, it's a sine equal to 1. The Coriolis acceleration equals, we substitute instead of sine 1, we can substitute the angular velocity, and we can the velocity of material of the relative velocity of the material point can specify. This is in the dependence. For any magnitudes, anybody can substitute here the magnitude of the velocity. I don't know, for the maybe for the fast speed air jet plane could be, I don't know, 200 meters per second. So if you multiply 200, so it will be the acceleration like about 0.03. So we have to reduce for the 100 and multiply by 200 meter is about 3 will be here. So 0.03 meters per second, dependent on the velocity. It's not big, but noticeable acceleration. And when they're moving of the point in direction tangential to the surface of Earth as the equator, so sine phi is equal to 0, the Coriolis acceleration is 0. So if the sine phi is equal to 0, Coriolis acceleration is equal to 0. So or it can move parallel, the sine phi be equal to 0. So the anyway, we can find here the Coriolis acceleration because the sine phi will be 90 degrees in this definite one location, and we will have maybe the same magnitude of as on the pole as on the pole. So we can find here the moving tangential to the equator direction. Oh, no. In any direction here we have the zero magnitude of the acceleration of the Coriolis. So next example, if we have the wheel rotating with angular velocity as shown on the figure 953A, and on the wheel we have the point moving with the relative velocity VR. So using the right screw rule for the product of the vectors, right screw rule, the transfer angular velocity of the moving is definite one wheel, and the translational velocity of the moving of definite one point in the point of the location, in the natural assignment of the motion of the point. So the reference point coincides with the definite point, and direction of the axis coincides with the direction of the velocity of the point. So what is the direction of the angular acceleration in any position? So the point first, the position of the point vertically down, so here. So we have the rotation of the wheel, the clockwise, watching here. So looking to the axis, we have two axes here on the plane, the abscissa and the ordinata axis, and we have the third axis. Third axis is applicata. Applicata directed towards the plane, of the scheme, and this axis applicata in direction, positive direction of the transfer angular velocity, that is the angular velocity of rotation of the wheel. This axis, the third one axis, goes beyond the screen, beyond the scheme. So what angle between the direction of the what is angle of the direction of the Coriolis acceleration? So we can use, for example, the Zherkovsky rule. The Zherkovsky rule is, if this is easy to use that, because if we have the axis perpendicular to the plane of the scheme, the axis we have, and this is the relative velocity translation projection on the plane perpendicular to the direction of the vector of the angular velocity directed beyond the screen. Then the projection on the plane of the translation velocity equal to the definite magnitude of this angular velocity, because it is in the plane perpendicular to the direction of the angular velocity transfer, omega e, sorry. So just we have to do the second step due to the Zherkovsky rule to rotate it in the direction of the rotation, rotate it in the direction of the rotation by the 90 degrees, angle of the 90 degrees. So we will have the direction of the Coriolis acceleration. In the horizontal on the right, we have the same. If we have the direction of the of the translational velocity upward here. It over the wheel, the point moves in the another direction. This direction of the rotation caused by the rotation of the surface of the wheel. In another way than the relative velocity we have. Then the projection on the plane perpendicular to the vector of the transfer angular velocity. This vector goes beyond the plane of the screen, beyond the plane of this scheme in the another one direction. So the magnitude of this relational velocity translation of the point M, the magnitude of the projection on the plane perpendicular to the direction of the transfer angular velocity is the same the same relative velocity of the point in the moving coordinate system. So we just do not need to do anything with this vector, just rotate it in the direction of the rotation of this wheel by the 90-degree angle and vehicle direction of the. So in any point, the Coriolis acceleration, in any point in the direction, the counter the rotation of the wheel, the motion of the point caused the Coriolis acceleration directed opposite to the normal acceleration. If the normal acceleration usually goes normal to the perpendicular to the tangential axis of the motion of this point, the normal acceleration directed here, then the Coriolis directed in the definite one case in this assignment, they counter the normal acceleration. Okay. So what next? Oh, okay, questions and comments. 951, complex movement of a point when there is a moving coordinate system which the point moves and the fixed coordinate system in which the moving coordinate system moves. The complex movement of the point means that we have the fixed coordinate system in which the point moves absolutely. Next, we have the moving coordinate system. The moving coordinate system movement of the coordinate system within the fixed one is the transfer motion. And besides the point moves in the moving coordinate system, that is, it is the relative motion of the point. That is the motion in the moving coordinate system. 952 relative motion of the point in the moving coordinate system. The transferring motion of point relative to the fixed coordinate system. When there is no relative motion of the point in the moving coordinate system and the point moves along with the moving coordinate system. Yes, if the point does not move in the moving coordinate system, then the relative motion of the point equal to 0 and the absolute motion of the point equal to the transfer motion. Transfer motion is the motion of the moving coordinate system within the fixed coordinate system. 953, the absolute velocity vector of point is equal to sum of vectors the transferring velocity, that is the velocity of movement of the coordinate system, and the relative velocity of point in the moving coordinate system. Yeah, nothing to say, just definition. As the next one, 954, the absolute acceleration vector during complex motion of the point equal to the sum of the acceleration vectors, the transferring, the relative, and the Coriolis acceleration, which the last characterizes the influence of the transferring motion on the relative velocity of the point and the relative motion of the motion transferring velocity. We just, for the last one, have to remember what is equal the Coriolis acceleration. So if the velocity in the complex motion corresponds, as in the item 953, correspond to the total of the vector total of the absolute velocity equal to total vector total of vector of the transfer motion of coordinate system and the vector of the translational motion of relative of the point is in a moving coordinate system. So the acceleration, absolute acceleration in the fixed coordinate system in the complex motion of the point equals to the acceleration, transfer acceleration of the moving coordinate system relative to the fixed one, and the relative acceleration of the point is in moving coordinate system. And besides, we have the third So the sum and vector sum and the Coriolis acceleration, we can find that as a doubled vector product of the transfer angular velocity of the no, of the rotation of the moving coordinate system relative the fixed one, and this is a first factor. So the 2 multiplied by the transfer angular velocity and multiplied by the relative vector of relative translational velocity of the point in the moving coordinate system. The acceleration vector is equal of twice the vector product of the vectors angular velocity of transfer and rotation of the moving coordinate system in the stationary system, and the translational velocity of the point in the moving coordinate system, that's the relative velocity of the point. Yeah, we told about that previously. 956. Absence of Coriolis acceleration during complex motion of the point when the moving coordinate system does not rotate in the stationary system, or when the point does not move in the moving coordinate system, or when the point of the moving coordinate system moves relatively along the line parallel to the angular velocity vector of moving system rotation relative the stationary system. This is understandable if we consider the equation to find the magnitude of the Coriolis acceleration. That's this magnitude equal to 2 multiplied by the magnitude of the angular transfer angular velocity of rotation of moving coordinate system in the fixed coordinate system, and the magnitude, next factor, magnitude of the relative translational velocity of the point in the moving coordinate system, and multiplied by sine of angle between the vectors of the transfer angular velocity of rotation moving coordinate system in the fixed one, and the vector of the translational relative velocity of moving the point in the moving coordinate system. So when the one of factors in the product equal to 0, then it can be if no rotation of the moving coordinate system is, or if the point do not move translationally in the moving coordinate system, and or the point moves in the moving coordinate system, but the movement is, or the point is translational moment is parallel to the rotation vector of the moment of the moving coordinate system and the fixed one. So this is the factors of the use or the equality of to 0 of the Coriolis acceleration. 957, the right square rule when find direction of the Coriolis acceleration vector, taking into account the vector product of the vectors, the angular vector transfer and rotation of the moving coordinate system in the stationary system, and the vector of the relative translation velocity of a point in the moving coordinate system. Yeah, if one rotates the angular velocity vector, transfer angular velocity of rotation of moving coordinate system in the fixed system, if we rotate this vector in the direction vector of the translation velocity relative of the point when the rotation axis parallel to the Coriolis acceleration, and the direction of the Coriolis acceleration along the axis correspond to the right screw rule when turning the angular velocity vector. So the direction of Coriolis acceleration coincides with the perpendicular, is on the perpendicular to both factors in the vector product as the transfer angular velocity of rotation of the moving coordinate system in the fixed one, the same perpendicular to the vector of the progressive translational velocity of the point in the moving coordinate system. Then on this perpendicular we can find the direction, another one having the rule is very convenient to use the right screw rule when we rotate the angular velocity transfer angular velocity rotate to the vector of the relative translational velocity in the moving coordinate system. Then the direction of the motion of the right screw coincides with the direction of the Coriolis acceleration. 958. The direction of the Coriolis acceleration vector determined by the n Zhukovsky rule. If one finds the plane perpendicular to the transference vector of the angular velocity of rotation of the moving system, and if the projects to the relative velocity vector of point of the moving coordinate system onto its plane, then rotating the projection of the relative velocity vector by angle of pi divided by 2, that is 90 degrees in the direction of the rotation of the moving coordinate system, one gets the direction of the Coriolis vector. This is just the technique how to find the direction by the Zhukovsky rule. Sometimes this is very convenient with the Zhukovsky rule. So 9 Coriolis acceleration when moving along the Earth's surface equal to 0 the equator, and the proportion to the velocity of movement of Earth's poles with a proportionality coefficient equal to twice angular velocity of the Earth's rotation equal to 2 pi per day, considering the day in seconds. So we can find the Coriolis acceleration independence on the latitude of the point, geographic latitude of the point, because the direction of the angular velocity of the Earth's rotation is from south to north pole by the axis of the rotation of the Earth. And having this vector, we next can find the direction of the vector, and the magnitude as well we can find considering the angular velocity, and the angle between the vectors corresponds to the definite latitude. So we can find, considering that the magnitude and the direction of the Coriolis acceleration is not big acceleration, but noticeable. It could be like maximal to as 0.0 about 3. So 3 hundredths, 3 of 100 parts of the meter per square second. About that, it's maximal possible, but noticeable. Yes, if you compare with gravity acceleration, this is much smaller, much lower. 9, 5, 10. The centrifugal direction of Coriolis acceleration from the axis of transfer and rotation. Yeah, the Coriolis acceleration usually directs counter the direction of the normal acceleration when we consider the point on the perimeter of the wheel, rotating wheel. So the natural acceleration directed to the center of the wheel, to the axis of the wheel rotation, and the Coriolis acceleration could be directed to the another side when material point moves along the rim of rotating disk. Thank you.